Hey guys, this is the corrections podcast for test 10, both the multiple choice and the free response. I'm going to be going through the free response first, the pulley problem, then the statics problem, then the angular momentum collision problem. Then I'm going to hit up the multiple choice, the ones that are most commonly missed. Now my goal with this is to kind of get you started. I won't get you all the way to the answer on all the parts, but hopefully get you enough to where you have some idea of how to work yourself on the corrections. So let's get going. Part A gives us the pulley and the block and asks us to draw a free body diagram on both of them. You guys didn't really do too badly on this one, actually. The one big thing that was missed was the force that was holding the pulley up. What a lot of people did correct was they said, well, I've got some kind of force of gravity down, I've got some kind of tension force up. You recognize that there was a tension pulling the pulley right there. You recognize that the pulley had some kind of mass, so it was being pulled down. But then you didn't think to yourself, well, wait a minute. If there's only two forces down, that means the pulley's going to fall off the thing. It's being supported. There's a force that's pushing it up. We're just going to call that like a support force. I accepted pretty much anything reasonable there. So we got our 3 points right there for the combination of that. But then the next bit asks us for the acceleration of the block. Now, the first thing of everything else, this is a linear acceleration. The block is falling down. But if we want to, there's kind of 2 points of attack here. Ayers' kids, this might not, I don't think it's the way Ayers taught it, but this is the way I'm going to do it because I'm making a podcast. The thought process here is this is a linear acceleration, but it's part of what the system is doing. In other words, the pulley and the block are doing the same thing. This is rotating while this is falling down. And it's actually a little bit easier if you treat this as a system and think about the pulley. So the first thing we're going to do is start off with the rotational version of Newton's second law. The idea that the acceleration of this is caused by the net torque on everything and the moment of inertia of everything. Well, neither of these are affecting the pulley directly, so we're going to ignore those forces. This force is not causing a torque because it's acting at the axis. This force is not causing a torque because it's acting at the axis. This force, however, is causing a torque. There's a moment arm there. There is a distance between the axis and the force. It's the radius. And then there's also a right angle, so we're going to ignore a little bit. And we're going to get to say that the torque on this pulley is going to be the radius times the force that's pulling it down. And since we're thinking the system, we're only concerned with forces from outside the system, which if we think about that, the only force here is the force acting on this force, on that box. That's the only outside force. So really what we have for our net force on everything, it's the weight of this one, which is M2. So all that's going to come together to give us a torque of, RF sine theta over the moment of inertia. The radius is actually the radius. The force that's pulling this down is M2G, and then a sine of 90. You got a point for expanding and getting your net torque right. We also have to deal with that moment of inertia, though. We're taking the system approach. We want to think about the moment of inertia of everything. Now, I straight up told you the moment of inertia of this was 1/2 times m1r squared. So we have that little contribution right there for the pulley. But then you notice I added a plus sign because we're dealing with everything, which means we need 2 moments of inertia. We need that moment of inertia. We also need that moment of inertia. That moment of inertia is acting like a point mass. So we treat it like a point mass. We treat it like it's one little box stuck on the edge right there, which it kind of is. So we're almost done. We're at the point where we have been able to write down that, let's make this a little bit cleaner, alpha is equal to that stuff. But let's think back to what I said a minute ago. We don't want the angular acceleration of the pulley. We want the translational acceleration of this, the tangential. Well, we know that there's a relationship between those things. AT equals alpha times the radius. Do a little bit of rearranging, plug it in. This turns into AT over R. At this point, we've pretty much answered the question. We have what we're looking for in our equation, and the rest of our variables are R, M1, and M2, and G, all of which we're actually allowed to use. Just to do a little bit of algebra to rearrange. And so once you do that, you're good, you're done. That's part A, that's part B, BI, that's 5 points right there. Now let's move on to thinking about just the tension in the core. Now you can do this 2 ways. You can focus here You can focus here. However, if you focus here, there is one mistake that basically everybody makes. The acceleration of this block is down. So you might be thinking that you can do Ft minus Fg equals ma. But the problem with that is that a is negative, and everybody forgets to plug in a as negative. So I actually think it's a little bit easier. Come back up here and substitute stuff in. In other words, we know that, again, the net torque on this, just the pulley, we're focusing on just the pulley now, is equal to I alpha. So we're actually going to get a point for starting off with that and focusing on just this. Well, the torque here, and remember, we're focusing on just the pulley now, so we're not thinking about that outside force, we're thinking about that. The torque is going to be just Rf sine of 90 is 1, equals the moment of inertia. Well, the moment of inertia is going to be the moment of inertia of just the pulley. So we have 1/2 m1 r squared times this angular acceleration. Well, we found a formula for the angular acceleration earlier in part B. So we're just going to throw that in there. Whatever we got earlier, we substitute that in. Then we do a little bit of algebra, rearrange some stuff, and solve for the force of tension, and then we're good. Now, some of you guys probably had that deer in the headlights look of, oh my God, the algebra in this problem. Yeah. One mistake we may have made this 2 year, we were too nice to you in terms of the algebra. As you saw on the mock exam, there are not a lot of exact numbers. There's a lot of equation and variable and algebra manipulation. You just need to be better at that. And so this rotation test is your chance to practice that. So you're going to obviously practice the big ideas here. So this is Newton's second law, the idea that some outside force is going to cause something to happen or whatever. But it's also being able to practice manipulating variables. Be careful with your subscripts. Only cancel stuff when it can actually be canceled. You'll get better at it. Okay, now I want to go on to the statics problem. And this one was kind of interesting. Because on the one hand, you could tell when people knew what was going on. A lot of people didn't, but you could tell when people knew what was going on because they started the problem right. They did a free body diagram thinking about the forces acting in this situation. They realized that there was a tension force up from the rope. They realized that there was a force of gravity down acting at the center because it's a uniform rod. And then they also were like, well, there's an axis. And then they thought to themselves something kind of nice. There's only vertical forces here. There's not going to be any horizontal force from the pin. If there were a horizontal force, it would just start moving the whole thing randomly. That's not a thing that happens. So there's actually only an upward force here from the axis. And so then they thought to themselves, well, I'm trying to find this. So I don't want to put my axis of rotation right there. I want to put my axis of rotation right here. And then this is the point where people either got a good grade on the problem or a bad grade on the problem. The people, let's get some glare out of the way. The people who got a good grade instantly started by writing this down. They knew that the net torque was equal to 0. There was a fantastically large amount of people who still wrote I alpha and then didn't realize that the angular acceleration was nothing. It's just sitting there. It's static. So we get a point just for saying that, for recognizing that this is in static equilibrium. Then we can start expanding stuff. We put the axis right here, so we don't care about that torque. The force is still there, but we don't care about the torque. This does have a torque. It's acting at a distance L over 2. A lot of people miss that. In other words, they tell us that this is L, which means this is L over 2. So if we're doing some torques here, this is the R. This is the distance from the axis of rotation to the force. So we're going to have a counterclockwise torque from gravity, that's positive, minus a torque from the axis, still equal to 0. Notice how I'm still writing equaling 0. I'm not forgetting the right side of my equation. This is going to be RF sine theta. Sine theta is going to be 90 in both cases, so we'll just leave that out. Got L over 2 times mg for that torque. And then for that torque over there, it's acting at a distance of L. And the force is a value that we don't know. And so if we think about what we know and what we don't know, we know that they tell us, we know L, we know f-axis. We're looking for f-axis. So we plug in the value that we know there as capital M, and then we do some rearranging, and we get a number, an expression, and we're done. And that's it. That's the whole thing right there. Recognizing that that net torque is 0, recognizing that that is half of the distance, and then doing algebra correctly. Most people missed points because of that. That sucked. You want to be careful of that. Okay, so then we burn the thread by a match. Well, all that's going to do is get rid of that. It's not going to do anything else. It's going to get rid of that strain. And so now we have to think about what's going to happen. Well, there's nothing holding it up anymore, which means now it is actually going to start to pivot. So we can't say that the net torque is 0 anymore. Now we're going to say the net torque is I alpha. And we're trying to actually figure out the angular acceleration, which means we need to kind of get rid of stuff that we don't know. And we don't know the force of the axis anymore. The reason we don't know the force of the axis is because it changed. That force went away, which totally rebalances the situation. So we're going to put that right there, and we're going to leave it. We're going to ignore the torque now. And so we can look and think about what's actually causing the torque here. Well, that's clockwise. So this torque is going to be negative. And so we're going to say negative RF sine theta. The R is, again, half the length. The force is, capital M, G, equals I alpha. So negative LMG over 2 equals I, well, they tell us that earlier in the problem. They say it's ML squared over 3 times alpha. We can do a little bit of wizardry here. I know you can do the algebra on your own later. Really, the only thing that I want to focus on is the fact that you can cancel stuff out. So you probably should. We're probably going to use this value later, so we want to cancel some stuff out and make our life easier. Don't go crazy if you're not comfortable with it. But you definitely want to get rid of some stuff. So we solve that for alpha. We get an answer. Then in part C, it wants the translational acceleration of the center of mass of the rod. This was actually a pretty easy question. A lot more of, at least my guys, you should have gotten it right. We know that tangential acceleration is equal to alpha times r. In other words, the linear acceleration of the center of mass is equal to the angular acceleration of the whole thing multiplied by how far away that spot is from the center. So I actually did have a decent amount of people get this and then do something with the value that they got in part B. They missed the R again. You've got to be careful with that. You're going to plug in here with your expression, your value from B, multiplied by a distance of, again, you guessed it, L over 2. Now, remember you have to write why you got your questions wrong. You're probably going to be writing, I used the wrong distance. Be specific there. Write that again and again so it really sears in your brain. That's a good thing. So we're going to get an expression. We now have an answer for AT. Now, you notice I'm not actually solving for the answers. That's your job. But just realize that at this point, we have a value for the acceleration. And so when part D asks us to solve for a force, well, we should be thinking, I just found an acceleration. I'm trying to find some forces. I'm going to do Newton's second law. I'm going to say that the net force is equal to the mass times the acceleration. Well, I look at this and I say, what's my net force? Well, I've got a force from the axis that's up. I've got a force from gravity that's down. So that f-axis, that's what I'm looking for, minus mg, again, I keep forgetting to plug in my capital M's, equals ma. Well, m is, like I said, capital M. And then a is just the answer to C. Plug that in, do one step of rearranging, there's your answer. Full points. Done. I do want to talk about the bonus. The bonus here was conservation of energy. The idea is that it starts off with some gravitational potential energy, but it then turns into rotational kinetic energy. So just putting down this, UG initial, is rotational final kinetic energy. That got you 2 points out of a possible of 4. Then you would expand that into equations, do a little bit of trig, and that's that. Okay, let's move on and talk about the big one, the angular momentum collision problem. This one I was actually pretty happy with. We gave this same problem last year, and it broke their very spirits. You guys did a lot better on it than they did, so props to you. The one nitpick I had was that some of you have forgotten what collisions mean. This was an answer you could just write down, so I'm just going to write it down. But then part B came, and it was like, derive an expression for the speed of the ball after the collision. Now, this is frustrating to both of us that we're still running into the issue of people not recognizing a collision. When you see a collision, ever, momentum is concerned. In this particular problem, it's a thing rotating. So, yeah, linear momentum will be conserved over like the universe. But in this particular thing, what we care about is angular momentum. So we need to start that off by saying all of the initial angular momentum turns into the final angular momentum. We've got to say that. And then we can start thinking about the actual collision aspect. But again, I can't stress enough, this is a collision. We have to use conservation of momentum. There's no other way. So initially, we said the momentum of the rod was this. The ball's not moving, so it doesn't have anything. So this is just 1/3 m1 d squared times omega. This is going to be the final momentum, final angular momentum of the whole thing. Well, again, with the values that we know, this is a point mass. It's moving with a linear momentum. So we make that an angular momentum by doing rp sine theta. Now, some people got to here, but they never dealt with that sine theta. You can look at that picture. It shows you which direction it moves. That tells you that sine, this is going to be sine of 90 and therefore 1. Rp, that's going to turn into, the radius is d, and then that's obviously mv. Let me double check that. That's going to be m2 times our final velocity that we're looking for. So we end up getting 1/3 m1 d squared omega equals that. It's worth pointing out, because a lot of you missed it, those cancel out. And so then we can rearrange for v. Now, a common mistake a lot of people did, this is right, by the way, this is the thought process, but a common mistake a lot of people made was back up here, they did this. They did I omega final. Now, that's not like an inherently awful thing to do. It'll get you to the right answer. But the problem was that a lot of people solved for this. But they said find the speed of the ball, not the angular speed. They want the speed of the ball. So you're going to have to do something with that. You need to, in other words, replace that with v over d. Realize I'm using v over r and saying that r is the distance they give us in the problem. So you want to be careful. Now I'm going to rewrite this, rewrite kind of our setup answer, because we're going to use it again later. So let's see. m1 d squared omega equals d into v. And now let's move on to part C. Assuming this collision is elastic, do some stuff. Now, we don't actually care that you can calculate the ratio here. We didn't give points for that. What we gave points for was that you knew what elastic collision meant, and you tried to do something reasonable with that. So we actually gave you 2 points, purely for writing down initial kinetic energy equals final kinetic energy. That was all you had to do. And then you had to think to yourself, well, initially, this was rotational kinetic energy. And then finally, it was translational kinetic energy. Or saying that the rotational initial was 1/2, I omega squared. So 1/2 times the moment of inertia of the rod, which they give us as 1/3 m1 d squared times omega initial squared. That was a point. Correctly getting the initial kinetic energy was 1 point. The final point, the fourth point, was for saying that the translational final kinetic energy was, and you're going to hate this, 1/2 mv squared, so the mass is in 2. And then the velocity is the answer from B. Whatever you got for the velocity in part B, that goes right there. That was the fourth point. This was purely a problem to see if you were able to understand elastic collisions and what they meant. And the answer was kind of a resounding no. So that's a thing that you're going to want to pay special attention to during these corrections. Not going to need that again, so I'm going to get rid of it. We'll move on to part D. And what they do in part D is very, very tricky. They just move M1. Sorry, they move the ball and they change its mass to M1. And they say, yeah, some other stuff happens, but the collision basically looks the same. So what's our new velocity? Well, we kind of already did this problem. We already got to here. Now, from a point standpoint on the AP test, please, please, please don't just copy this equation back down. Show where you're getting this equation first. In other words, you needed to write this again. You needed to use you needed to make it clear that you were using conservation of angular momentum. But then once you did that, you get 1/3 m1 d squared omega. That's not going to change. And then this turns into a new distance. Well, that new distance is now not d. What do they say? It's x. By the way, notice how I said not to scale right there? That means that it's not to scale. So yeah, I know that it looks like half the distance, but don't make that half d. You don't know that it's half d. So we leave that x. Now the mass of the ball is m1. Its final velocity is v. There we go. Solve some stuff, we're done. A relatively straightforward problem. And then write an equation that supports the claim that this collision is elastic. Well, again, we already played this game. This is getting a little bit old at this point. The equation that supports this claim that the collision is elastic has to start here. That's what it means for a collision to be elastic. This is the statement that proves a collision is elastic. If this is not true, it is inelastic. But we think that this is true, so we're going to start here and then see if it works. So this, again, we have 1/2 I omega squared. This is still, 1/3 m1 d squared times omega initial squared. That was 1 point for getting the initial right. And then, actually no, excuse me. It was the first point is for this, the second point is for getting this whole, both parts right. And then this is going to be 1/2 times m1 times the answer to d squared. Again, didn't actually care about what else you did with this. Just that you could understand that this collision being elastic means this. Now again, I want to come back to the fact this is a really hard test. It factually is a challenging test. They're hard problems. But let's think about the 3 free response problems and the principles that we've had to use. We've had to recognize when Newton's second law was a thing. That's not new. That's a thing we should be able to do. We should be able to recognize that a net torque will cause an acceleration, or a net force will cause a linear acceleration. We should be able to recognize that when 2 objects collide, momentum is conserved. And so we start with that, and then as silly as this sounds, we just kind of start plugging stuff in and see where it takes us. We plug in the values and the expressions that we know. We don't get scared because they're variables. That's a skill that you get better at. You might be intimidated by the variables, and that's kind of okay. Got about a week and 2 days to get over that. You'll get there. Fall back on big physics ideas. That's what the Physics 1 test is all about. Recognizing when big ideas are applicable. So it's the difference between seeing this picture and recognizing that it's going to spin. It's going to angularly accelerate. So we need to use Newton's second law versus seeing this picture and recognizing that it's hanging, and therefore we're not going to talk about acceleration. We're going to say the net everything is 0. That's our thought processes here. Okay, so we are done with the free response test. We're going to move on to the multiple choice test now. Now, I'm not going to cover all the problems. And remember, I unfortunately will not be available next week in the mornings because I'll be taking care of my Physics 2 students. So if you have questions on any of the other ones, you need to come after school sometime, realize I'll be doing review sessions, or find errors. I'm going to start off with number 5. Number 5 was kind of tricky. It's a string of length L. Maybe a rod of length L. And they said it was spinning about the center. And it had a certain moment of inertia. And then there was a point mass right here of mass m. Well, a lot of people correctly said that the total moment of inertia is going to be the moment of inertia of the rod plus the moment of inertia of the point mass. It is. They tell us that this is I naught, and this is going to be mr squared. The mass of the point mass is m. However, the r, this distance, is L over 2. In case you couldn't tell, that was a theme I cared very heavily about as I made this test. I wanted you to be able to recognize when the distance is half or whatever. You've got to be conscious of that. Number 6 is next. We're trying to find the angular acceleration about the point that they mark for us. And so this becomes an issue. This becomes an issue of Newton's second law again. It's that same thought process of recognizing that the net torque from these objects is going to cause an angular acceleration. Now, to be kind of nice here and break this down into steps, we've got the left object and the right objects. The left object's torque will be positive. So we say the torque from 3m minus the torque from m all over the total moment of inertia. In other words, the moment of inertia of the 3m plus the moment of inertia of the m. It's about to get real ugly. I'm sorry. The torque from the first one, we have a distance of L times a force of 3m naught g sine 90 minus a distance of 2L times m naught g. All of that over mr squared for both of them. So this one is 3m naught times L squared plus m naught plus 2, or times, times 2L squared. Now let's do some simplification here and make this look a little bit less scary. We see L m naught g, L m naught g. So let's combine some like terms and realize that this top part is going to end up being just 1 L m naught g. And then down here, we have 3 m naught L squared plus just m naught times 2 squared L squared, 4 L squared. So we have 3 and 4 of the ml squared. We're going to combine those and make 7. From here, you should be able to do the rest of the thing. Cross some stuff out, find the answer that matches. This one was challenging, but again, it's worth being able to do this algebra. Okay, number 7. We're trying to find which of these torques cancel out. Now, one thing that was awesome to see, basically everyone picked C and D. Their thought process was, they were understanding things relatively correctly. But the choice between C and D is a matter of angles. And when a lot of you plugged into your calculator, you realized that if the force was 2F and the distance was still L, that sine of the angle had to be 1/2 to cancel out that 2. Problem was that's not the scale, sorry. You didn't think about the angle that they gave you. We need the angle between the force and L, between the force and the rod. In other words, we don't care about that 60. We care about that, oh my God, that was embarrassing. We care about that 60 plus 90 giving us 150 degrees. We don't care about the angle between the rod and this. We care about the 60 degrees. We care about the angle between the force and L. Only one of those, the sine of that angle, gives you the right thing. Okay, on to number 10. Number 10 was one of the only just pure rotational kinematics problems on the test. And it was based off a formula that wasn't on the formula chart. This formula, however, is on the formula chart. V final squared equals V initial squared plus 2A delta x. And so you might find it unreasonable, but yeah, I did want you to realize that you can just do this. Both of us gave you this formula, and even though it's not on the formula chart, we tried to get you pretty good at understanding that you could just boom, 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 boom. And so they say, what do they say? It's initially at rest, so that goes away. We're looking for that. We're saying it's just alpha. And then this is 1 revolution, so it's 2 pi radians. Plug in and solve. 13 was another commonly missed one. In the interest of not having this go on for 16 hours, I'm not going to key it out. I'm sorry. It's in your notes. Both of us covered it. Realize that this is conservation of energy. The maximum vertical height to which it can roll if it ascends an incline that has friction means that it starts off with rotational kinetic energy and translational kinetic energy. Since there is friction, it's able to lose its rotational energy. In other words, if there was no friction, it would keep spinning as it moved up the incline and then fall back. However, here it's rolling, 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 slows down to a stop, and so all the energy turns into potential energy. So that's that. Plug in and solve. 1/2 I omega squared, 1/2 mv squared equals mgh. Remember that you can relate v and omega through this equation. That's pretty much that. Moving on, number 14. This was surprisingly one of the more missed ones. We actually thought this would be one of these, slightly easier questions. We're trying to find the pulley's rotational motion, an equation that describes the pulley's rotational motion. We're told that this is a tension 2, this is a tension 1, and we're told that the radius of the pulley is r. So we know that net torque is equal to I alpha. The net torque is, let's see, this is clockwise, so it's negative. This is counterclockwise, so it's positive. So tau 1 minus tau 2 equals I alpha. This torque is RF sine theta, so R times T1 minus R times T2, theta is 90 for both of them, equals I alpha. Now at this point, we look on the sheet or the answers, and we'd say, well, all of those are they're all I alpha, so I'm going to ignore that and leave it alone. I'm going to factor R out of here and get R T1 minus T2 equals I alpha. There we go. Now, looking at this, we see that only one of them has T minus T anything, but it's the other way. And so we think to ourselves, well, I have an answer that based on my understanding of physics and based on what I chose, my positive and my negative, looks almost right. And it looks nothing like any of the other answers. So your thought process here is, well, either they picked the other way to be positive, or you're completely wrong. It's a lot more likely they just changed their positive and negatives. In other words, they said that this was positive, or we already said that. They said that this was negative and this was positive, which is going to change the signs. That's still the same physics, though. Just changes the sign of your angular acceleration. Don't stress too much about that. Number 17. All right, first thing is that has a length of a. I need you to be comfortable with that. If that coordinate is 0 on the x and a on the y, that distance is a. Well, then the next thing is to realize that if we're trying to find the angular momentum about that point, we say L equals R mv sine theta, where this is our R, and that's the angle between the two things. Well, we have R, we have M, we have V. Sine theta, though, goes that way. So it's the opposite over the hypotenuse. Now, something kind of crazy is about to happen. R in V, sine theta, remember we said it's opposite over hypotenuse. The opposite side is A. The hypotenuse, that's R. There's our answer. Number 18. We're almost done. Second to last one. Asks for the ratio of some angular momentums. So we want the L on the top over the angular momentum of the bottom. Let's expand. I omega over I omega. This is top, this is bottom. Let's think about those omegas though. They say it rotates rigidly, which means they both have the same angular velocity. That goes away. And so our I total is going to be 2 times the two little thingies on top over 2 times the little thingies on the bottom. All right, that's what that makes sense. 2 times the top things, 2 of the bottom things. So at this point, we can cancel out the 2 because we know that we're really just finding the ratio of 1 of the point masses. Okay, well, one of the top things has a moment of inertia of little m times L squared. It's rotating around the center, a distance L away from the center. The other one has a moment of inertia of its mass is 2m times a distance of 2L squared. So we get mL squared over 2m times 2 squared L squared, 4L squared. The L squareds cancel out. The m's cancel out. We're left with 1 over 8. Y'all did pretty well in 19 and 20. You should be proud of that. And now finally, number 23. I don't have to write anything about this. The logic here is that as the ice skater is spinning and pulls in, she speeds up. Her angular momentum stays the same. That's why she speeds up. But let's think about the kinetic energy. I said I wasn't going to write anything. I lied. Both of these are changing. The moment of inertia goes down. The velocity goes up. Their factors are the same. In other words, if we divide this by 2, we're going to multiply this by 2. But that one's squared. So this value actually wins. This is the dominant effect. If this divides by 2, this is going to get multiplied by 2 squared. So the rotational kinetic energy is actually going to get bigger. That energy, by the way, comes from her doing work to change her moment of inertia. She has to do work on herself. She's converting the chemical energy in her muscles to rotational kinetic energy. That's where that's coming from. Okay, so these corrections are going to be due on next Friday. Let's see, that's the 29th-ish, something like that. Get them in. You can work on them at home. Let's get it taken care of. See y'all tomorrow.